Okay, here are our Y situations. A 20 kilogram elf stands on a scale in an elevator. What does the scale read in newtons when the elevator is? And we have a bunch of situations that we're going to try all of. I'm going to minimize this slide so that I can talk about it and write next to it. This problem gives me forces, newtons, and I see that at some point it mentions acceleration. So this is a Newton's second law problem, and your brain should say F net equals ma. If we look at our elf for a second, we can tell what forces are acting on him. He has gravity pulling down and a normal force keeping him up, and he doesn't have any forces left or right. He only has y forces. So I'm going to go ahead and say that we're only dealing with y forces here. And I could show that just like I did in the last two examples, but I have a bunch to work through, and so that would take a long time. So what I'm going to do is say, look, I know there are no x forces, so I'm only going to deal with y. Now we need to know what all of those y forces are. He has gravity pulling him down. Down's negative. Normal force keeping him up. I'm just going to do n for normal force. We can find his force of gravity, his weight. He's a 20 kilogram elf. That's a mass. Weight is mass times gravity. So mass, 20 kilograms. This problem is happening assumedly on Earth. The gravity is 10 newtons per kilogram. 20 times 10 is 200, so his weight is negative 200 newtons. Plus, we also have his normal force. Now you might think to yourself, if he's at rest, that's static equilibrium. We're working the first problem. And I could find the normal force. Yeah, you already know enough to find that normal force right this second. But because I want you to get used to Newton's second law, I'm going to do this as a second law problem. Remember that F net y equals mass times acceleration. We're looking for the normal force, which is part of F net y. So I need to take this F net y and sub all this stuff in right here. Negative 200 newtons plus the normal force equals mass times acceleration. Now I'm going to solve for the normal force. To get normal by itself, I need to add 200 newtons to both sides. Normal force equals mass times acceleration plus 200 newtons. We know his mass and his acceleration, so normal force equals 20 kilograms. He's at rest, so his acceleration is 0 meters per second squared plus 200 newtons. Anything times 0 is 0, so his normal force is what's left over, 200 newtons. That's the normal force. Check and done. Next, in these two other situations, he still has no acceleration. Here he's moving at a constant 3 meters per second, and then again at a constant 3 meters per second. In one of them he's going up, in one of them he's going down. But he has no acceleration. And so when we work out those problems, we'll get the same answer as we did here, because acceleration is 0. So we've already answered the first three. You can also remember from static equilibrium that as far as forces are concerned, being at rest is the same thing as moving at a constant speed. And so anytime you solve a problem for at rest, you've also solved the problem for moving at a constant speed. Now let's go on to the next three parts of this example. So now let's look at the situation where the elf is accelerating upward at 3 meters per second squared. If he's accelerating upward, upward is positive, so AY is 3 meters per second squared, and that's positive. This is still a Newton's second law problem, so my brain's going to go F net. And I made the argument on the last slide that we're only dealing with y forces. F net y equals mass times acceleration in y. Okay. The net forces on the elf, he still has gravity working on him. He still has a normal force on him. Gravity points down, normal force up, therefore gravity is negative. Normal force is positive. And his weight, his Fg, his mass didn't change, so that's still F net equals. We can find that weight. He's still a 20 kilogram elf. His mass hasn't changed. Gravity on Earth hasn't changed. So so his weight is still 200 newtons, and that's still pointing down, so it's negative. We're looking for the normal force. Okay, so now let's take this information here and plug it in for F net in our original equation. Now we have negative 200 newtons plus our normal force equals mass times the acceleration in y. He is accelerating upward at 3 meters per second squared, so we know acceleration and we're trying to find normal force. Let's solve for the normal force. I'll add 200 to both sides, just like last time. Normal force equals mass times acceleration in y plus 200 newtons. Normal force equals 20 kilograms, his mass. His acceleration in y is 3 meters per second squared from up here, plus 200 newtons. Solve that through algebra. Now we have normal force equals 20 times 3 is 60. Remember, kilograms times meters per second squared are newtons, so 60 newtons plus 200 newtons. His normal force is therefore 260 newtons. Check. That is the normal force when the elf is accelerating upward at 3 meters per second squared. And that should be a squared. That 2 did something weird. Moving on to the next one. Okay, next example. He is now accelerating downward at 3 meters per second squared. If he's going down, that's a negative, so negative 3 meters per second squared is our acceleration in y. Everything else, except for that sign, is pretty much the same as the last one. So let's see if we can do this fast. Net forces in y equal mass times acceleration in y. My net forces in y, oh, it looks like my free body diagram went away. He has gravity pulling him down, normal force keeping him up. Remember, I made the argument 2 slides ago about why there are no x forces. So he has negative weight, positive normal force because of the way they're pointing. His mass has not changed, and so his weight has not changed, plus the normal force. We're going to sub in this F net up here, so negative 200 newtons plus the normal force equals mass times acceleration in y. Solve for our normal force. Normal equals mass times acceleration in y plus 200 newtons, just like before. We know his mass, 20 kilograms. His acceleration in y this time is negative 3 meters per second squared, plus 200 newtons. 20 times 3 is 60, and it's a negative 3, so negative 60 newtons plus 200 newtons. Negative 60 plus 200 is 140 newtons, and that's our normal force, which is also what the scale he's standing on reads. Now we're down to our last example. Here we go. So our last example is a pretty interesting problem because of what we're going to find out about the way things work on Earth. So we still have gravity down, still have a normal force up. We made the argument that we're only dealing with y forces. This time our acceleration is downward, negative 9.81 meters per second squared. And yes, the fact that that's the same as gravity is going to mean something. It's pointing down, negative 9.81 meters per second squared. And since we call gravity about 10, let's go ahead and say that this is also about 10. Just because I want you to see what it means when you have an acceleration downward that's the same as gravity. Okay, here we go. His forces in y are weight pulling him down, normal force pushing him up. We can find his weight, which we've done several times, so that Fg becomes negative 200 newtons plus a normal force. We now rewrite our original equation using this. F net is negative 200 newtons plus a normal force equals mass times acceleration in y. Net forces equal mass times acceleration. Move that 200 over, normal equals mass times acceleration in y plus 200 newtons. All right, normal equals 20 kilograms. We said the acceleration in y is about negative 10 meters per second squared, which again, yes, is the same as gravity, plus 200 newtons. 20 times negative 10 is going to be negative 200. Negative 200, this right here, plus 200 is 0 newtons, and that's your normal force. If you are ever falling with the acceleration of gravity, that means nothing is holding you up, and so your normal force is 0. So if you were to ever jump out of an airplane and try to stand on a bathroom scale successfully while falling from the airplane, your normal force, that scale, would read 0 because nothing is holding you up. You are simply falling. And that, my friends, is called free fall, which we have talked about before. You're simply falling. Anytime you have no normal force and there's nothing else holding you up, no tensions or anything, that's free fall. And that's also our final example.